In this video, we're going to run through examples of how to do an independent t-test and then a paired or dependent t-test. So we'll start by loading up our data and our packages. We're going to use the Pacman package to do that. This first line just ensures the Pacman's installed. Second line will load up the tidyverse from CRAN. This line will load the latest version of example data. So we run those three lines. And let's have a look at the t-test function. It's a built-in function in R, and it's a pretty powerful function. It can do both paired or independent and dependent or paired t-tests. To do that, you just use paired equals false or true. By default, it assumes unequal variances, so results that you typically would get in a book, this may be slightly different because R uses a little more robust version of the t-test. Okay, let's get started. We're going to be using the Wegmans data set. And we have two hypotheses we're going to be testing out. The first is comparing foreign and domestic, so that's product of USA, comparing whether there's a difference in new prices for those two groups. So these are independent groups. And the second one is there a difference between average new and old price? And that is a dependent test because we have items that have changed at two different times, right? So the null hypothesis is that there's no difference for both of these, and the alternative hypothesis is that there is indeed a difference. So the first thing we're going to do is clean up some of this data, and we want to turn product of USA, we want to turn it into domestic and foreign, right? So I'm just going to select the columns I want right off the bat. So I know I want these three columns for this. I'm going to take product of USA, I'm going to use a case win on it, and I'm going to say whenever it's product of USA is 0, that's foreign. Everything else is domestic. So I went ahead and made a subset of data here, and that's what I'm going to be using. I'm going to calculate some summary stats. That's typical of an analysis. And I'm going to calculate standard errors. There's a nice little function for calculating standard errors. R doesn't have a built-in way to do that, but it's so simple to compute. It's just the variance divided by the length of x and then the square root of that whole thing, right? So I'm going to group by product of USA in our small subset of data, and I'm going to summarize, get an average, standard deviation, the n, median while I'm at it, and the standard error. You see that computed that information is pretty quick, pretty nice way to do it. I'm also going to go ahead and take the new and old prices, and I'm going to tidy them up. I'm going to just gather them into one data set, calling the first column time. I'm going to stack the variable names, and then I'm going to stack the prices themselves as a price variable. Let me see what that looks like. And I'm going to go ahead and use the same summary stats on that. And we can see that there's very little difference in the averages, standard deviations, ends, medians. They're all pretty much identical. So I don't really expect a statistical difference between these two. Though given a large enough n, almost anything will be statistically significant. All right, let's go ahead and start by visualizing the difference. We're going to start with the foreign and domestic groups, right? And there's a number of ways we can do this. We can, if we're looking at distributions, and that's really what we're looking at, we're looking at distributions of prices for these two groups. Box plots are an excellent way to do that. So we can tell it product of USA is my X variable, that's my grouping variable, and new price. And it will calculate the 5 summary stats it needs for a box plot on the fly. And we want to get a little fancier, we can use stat summary here, and we can add the means as well. So that can be nice. We can see there's a slight difference, not a huge difference, but there's kind of a slight difference, but there's some variability in the two data sets. The distributions are not normally distributed. We can tell that because the box, the center median, is not in the center of the box. If it was, it would be a little more evenly distributed. And then you can also see, so that's the 25th and the 75th percentiles, the quartiles. And you can see that the extreme tails here, the whiskers here, they would also be equal if this was more of a normal distribution. Okay, we can also use histograms to visualize differences in distributions. And I've done this here, I faceted out. So you see that I filled by product of USA, and then I faceted by product of USA. It's kind of hard to compare if they're equal or not, so something that we can do by adding stat equals density here instead. And you can see that I've already plotted that over there to the right. With this small number, though, there's a lot of smoothing going on that might not be the best choice. We can also compute frequency polygons to look at the distributions. Similar type boilerplate here. The distributions look very similar. We can also use density plots. has similar smoothing problems with such a small sample though. So I'm going to ask you to pause the video, take a turn visualizing the data set though, this time for old price versus new price, the time, and those prices, and compare their distributions. Okay, so maybe you came up with plots like I have here. I created box plots, almost identical distributions. Doesn't imply that there'll be much of a difference for those two distributions. Create histograms faceted here, and you can see again the distributions are almost identical, even the variability very similar. Okay, let's move on to a test of significance, and we're going to start with the first hypothesis where we're looking at foreign and domestic. And here I show you how to compute it by hand. Mostly I do this so that you can appreciate that R has built-in functions, but also realize that, hey, this could be computed by hand. Basically, you're computing pooled standard deviation, which is right here, and you take the difference between means, and you divide it by that pooled standard deviation. Let's go ahead and run that. This formula is very similar to the formula found in field, and you'll see that we get negative 0.636. If we wanted to look that up, we can go to a table online of t-tables. Degrees of freedom for this is total n of the two groups minus 2. You burnt 2 degrees of freedom there, so it's 30 minus 2, so 28. And you come out to, we want to do two tails at 0.05 right here, so we needed a value that exceeded 2.048. And this doesn't even remotely, and that's the absolute value of that is, and it doesn't even come close to that. Now we can do a built-in t-test, and we can use t-test here, and we can use a formula. The first thing we pass to it, well, we give it data over here, if you notice, and that's the small subset of data we had, and we give it a formula, and the tilde is how you give it a formula, and y is your first thing, tilde by product of USA. And this is really useful because this follows the same boilerplate format for all formulas in R. And so we tell it the outcome by the predictors, and the predictors are product of USA. So we run that, and we see we get relatively close to our t-value, but not exactly the same. One thing to note that this is by default R is using variance assumed not to be true or equal, and if you want to force R to use variance equals or equal variance, you would set that variance dot equals true. Probably not so useful. That's why it's not the default. One thing you do notice by doing that though, the degrees of freedom winds up being not an integer value. You see it also gives you a nice p-value here. It gives you your t-stat. It gives you your confidence intervals, which do contain 0. So it also gives you the group means here as well. So this is the Welch's two-sample t-test. We can run it with variance equals true, and that's just the two-sample t-test. We can see slightly different values. Degrees of freedom is 28, but overall not too much of a difference in any of the statistics created. So I'm actually going to delete that line because it's not really the recommended approach. And to write that up, we could use something along the lines of Wegmans domestic, and then you give the mean and standard deviation. Items were not, on average, any cheaper than foreign products, and I give the mean and standard deviation with a non-significant difference of t, and in 28, that's the degrees of freedom, equals negative 0.62. That's the t statistic, and then the p-value, since it's not less than 0.05, I get the exact p-value of 0.54. So how do we do where we have paired groups? So the first thing I'm going to do is create some stats for that. Actually, let's look at W price here for a second. I just want to jog your memory. That's our subset, and I'm going to grab just product of USA. And then I want to go ahead and say, I want the difference between old price and new price. I'm going to create new columns for that, and I'm also going to do D squared, that difference squared. I'm going to use these to compute difference in paired samples, or dependent samples. And we can see some stats here I'm using where I creating some basic summary or basic computations. Those are all fairly simple. And this is where it gets slightly more complicated. This is where you'd be more likely to make a mistake. I'm going to run that. Not so important that you understand how to do this by hand, but I want you to realize that it can be done by hand. Andy Field gives examples of how to do it by hand, and you can see that indeed we can do it by hand. but you can also see that you're much more likely to make a mistake when you do it by hand. R has some built-in t-testing for this as well. Same exact process that we used above, except for we're adding in paired equals true. Okay, and we give it the small data set, the stack data set here, where time and price, and we say price, that's the outcome variable, and the predictor is time. We run that, and we get almost exactly the same t statistic. It's essentially 0. Degrees of freedom is 29. P-value is near 1. Basically, these are the same prices. And the write-up on this for a paired sample like this, something along the lines of the 30 items had on average difference from old to new repricing of less than a ½ cent decrease, indicating the new prices were not any cheaper in general than the old prices. And then I give the t-stat, t with 29 degrees of freedom. For the paired, you actually have n minus 1 for degrees of freedom equals your t-stat, which is 0 in this case, p of 1. So essentially these two values are pretty near the same. So this video showed you how to do the dependent and independent. I guess I did independent first and then dependent sample t-tests in R.